In this section, we'll compare beam search and greedy decoding in the context of LLM jobs and real production systems. The goal is to understand not just how these strategies work, but when each one actually makes sense. We'll look at the trade-offs in quality, speed, and cost, and focus on the kind of practical reasoning employers want to hear in interviews and on the job. Here's the roadmap for this section. We'll start with the core problem, why greedy decoding often misses better overall sequences. Then, we'll walk through how beam search works, including the basic algorithm and the key controls behind it. After that, we'll look at the trade-offs and common failure modes, so you know when beam search actually helps. Finally, we'll connect it to career strategy, including interviews, portfolios, and practical use on real projects. Greedy decoding has a simple weakness. It's myopic by design. At each step, it picks the single most likely next token and never considers where that choice might lead. The problem is that the best local option isn't always the best overall sequence. And once that token is chosen, every other possible path is thrown away. So greedy decoding is fast, but it can easily miss better, more coherent results. Here's the key difference between greedy and beam search. Greedy decoding picks the single highest probability token at each step, so it explores very little and can end up with a lower probability overall sequence. Beam search instead keeps several likely partial sequences alive as it goes. That gives it more exploration and usually more confidence in the final result, because it chooses the sequence with the highest total probability, not just the best immediate next token. Beam search works by keeping several possible sequences alive at once. At each step, the model expands each beam with its top token options, scores those candidates, and then prunes back to the best n beams. That repeat expand, score, prune cycle continues until the sequences are complete. The key setting is beam width, or num beams. One gives greedy decoding, while larger values search more broadly, often improving results but increasing compute time and latency. Here's the quick mental model for Hugging Face generation settings. If numbeams is 1, you're doing greedy decoding. Set numbeams above 1, and it switches to beam search. If doSample is false, the output stays deterministic. For stopping behavior, early stopping set to true ends generation when all beams are done, while never keeps searching until the best result is found. These are the core knobs you should know instantly in an interview. In production, beam width isn't the only setting that matters. It's the main quality versus compute trade-off. But the best results come from tuning it alongside 3 other controls. Stopping criteria determine when search ends, affecting both speed and output quality. Score normalization helps avoid unfair bias toward shorter or longer candidates, and hypothesis filtering removes clearly weak options. In practice, strong decoding comes from balancing all 4 together. Chapter 2 is about the core trade-off in beam search. As you increase the number of beams, you usually get better sequence-level search because the model keeps more candidate paths alive. But that improvement comes at a cost: more computation and higher latency. So the real engineering question is where to set that balance for your task. Knowing how to make that judgment is exactly what employers want to see. This slide shows the trade-off between output quality and latency as beam size increases. Early on, using a small beam can improve quality quite a bit, but those gains start to level off quickly. At the same time, latency keeps rising, often faster than quality improves. That's why beams in the 2 to 4 range often capture most of the benefit, while larger beams can actually hurt performance, a pattern known in NMT as the beam search curse. Beam search tends to work best when there's a fairly clear target output, and the model's overall sequence probability is a good signal for quality. That's why it's a strong default in machine translation, like in OpenNMT, and often useful for summarization as well. It also fits structured or constrained generation, where the search space is narrower and choosing the highest likelihood sequence is more likely to produce the right result. Beam search isn't always the right choice. For open-ended chatbots, sampling methods like TopCag or TopTag usually sound more natural and conversational. The same goes for creative assistants, where variety and unexpected phrasing are actually strengths, and beam search tends to work against that. And in high-volume, low-latency APIs, running multiple beams adds real compute cost fast, which can make production systems more expensive and less efficient. One important failure mode is the beam search curse. Intuitively, you might expect a larger beam to always help, but in practice, it can actually hurt output quality. A wider search amplifies whatever scoring bias the model already has, so bad completions can rise to the top more reliably. The key engineering lesson is that search and model behavior are coupled. Good models with good search work well, but biased models with wide beams can make errors worse. Chapter 3 is about what employers actually want. In LLM and AI engineering interviews, people usually care less about textbook definitions and more about how you think. Can you make smart trade-offs between quality and latency? Do you evaluate systems in a disciplined way? And do you understand what it takes to make something reliable in production? That practical judgment is often what separates strong candidates from everyone else. Here are the key interview questions and answers on beam search. Compared with greedy decoding, beam search keeps several partial sequences instead of committing to one token at a time, which usually improves the final result. The trade-off is more compute and latency, with smaller gains as beam width gets larger. It's usually not ideal for open-ended generation, where sampling sounds more natural, and when tuning it, adjust beam width, stopping rules, and score normalization together. A strong portfolio project follows a simple, disciplined structure. First, define a clear task, like translation, summarization, or structured generation. Then run a comparison. For example, beam search with num beams set to 1 versus 4, and measure latency. After that, analyze the outputs using both qualitative review and basic metrics, including beam indices. Finally, write everything up: the settings, results, failures, and your judgment. That process showcases debugging, evaluation, and practical LLM engineering skills. A strong write-up on beam search needs 4 things. First, define the task and explain why beam search actually fits this problem. Second, report your decoding settings clearly, including the number of beams, when decoding stops, and any normalization choices. Third, measure results rigorously with examples, task-specific metrics, and runtime. And finally, show judgment. Be honest about where beam search helped, where it fell short, and what you'd improve next. Here's the quick decision tree I'd use in practice. If the task is open-ended, like chat or creative writing, use sampling to keep outputs varied and natural. If latency matters most, go with greedy decoding. For structured tasks like translation or summarization, beam search. Usually somewhere between 2 and 8 beams is a solid default. And most importantly, always evaluate on your actual use case instead of assuming one strategy is best. Beam search is useful, less as a formula to memorize and more as a mental model. Instead of making one greedy choice at each token, it keeps a few strong candidate paths and compares overall sequence quality. That introduces a trade-off. Wider beams usually improve results, but they also add latency and cost. So in practice, the right decoding strategy depends on the product experience you're trying to deliver, not just the algorithm on paper. This is really the bigger career play. Learn decoding as a form of inference engineering, where model behavior connects directly to user experience, cost, and evaluation. Then build projects that show judgment, not just generating outputs, but implementing, measuring, and explaining your choices. That's what signals production readiness. When you understand tuning controls, you move beyond toy demos and start building systems that can actually hold up in real pipelines. Here are the key takeaways. Beam search usually beats greedy decoding on constrained tasks like translation, summarization, and other structured generation problems because it finds stronger full sequence outputs. But in practice, beam width is only one tuning lever. You also need to think about stopping rules and length normalization. For open-ended tasks, sampling is often better because diversity matters. And in interviews, strong answers focus on trade-offs, evaluation, and real implementation experience.